Okay, so we're going to keep going into the fundamental theorem of calculus and connecting that to area. In the beginning of the school year, I said that calculus is the bridge between geometry and algebra, and this is really where you start seeing that, because we're going to be playing with area a lot, and you're going to be seeing how the functions and their areas tie into these integral statements. Okay, so if we're finding the area of a strange-looking space via a formula, we're going to be looking at oblong-looking areas like this. Versus in geometry, when you're looking at simple areas, like, for example, squares, diamonds, circles, things like that. Now what we're going to be doing is giving you all a tool to find areas of oblong shapes given functions. Okay? So the definition of a definite integral is if f is a non-negative continuous function on the interval a to b, the area of the region bounded by the graph of f, which is the function, the x-axis, and the lines xa and xb are denoted by this, okay, which is the integral of a to b of f of x with respect to dx, okay? This is called the definite integral because we have defined bounds. Oh, I didn't change this from last time. Hold on, guys. I'm not going to stop. Just going to edit for my life. Oop. Doesn't like me. Oop, oop, oop. There we go. Back in action. Okay. So the expression a, the integral of a to b f of x dx is called the definite integral. Okay, where the lower limit is the number that's on the bottom, that a, and then the upper limit is the number that's on the top. Okay, so in simpler terms, like if I break this down, the value of that definite integral from point A to point B is the area underneath that curve. Now, this is a very, very powerful tool if we think about like what is it that graphs do. So graphs, in and of themselves, represent relationships between two variables. So if we're talking about an area, what we're talking about is a accumulation of two different variables. So for example, if we were graphing a population function, so for example, this f of x was a population, and then this b was time, this area would be a population over time, where our derivative would tell us the rate at which that population is changing. The integral actually tells us how much population there is at over a certain span of time, which is, in my opinion, more powerful than the derivative in terms of a data science application. Okay, so this is where the fundamental theorem of calculus comes in, is because this is what gives us that tool in order to take that area. So we have the definite integral of a to b f of x is equal to f of b minus f of a, which is the evaluation of that integral statement. Okay, so where f is any function of such that f prime of x is equal to f for all of x in the definite integral a b. Okay, so that is stating that the f of x in the integrand, the integrand is a derivative. So this here is a derivative. The integral is still an inverse function, and we have to still find an antiderivative in order to solve. So if we're not finding an antiderivative here, we're not doing the right thing. Okay, I don't want you to approach this in a visual sense, even though I'm giving you visual tools. But sometimes looking at a visual will help you see an approximation of what your answer should be. But I don't want you counting the squares, because that's just going to give you a wrong answer. Okay, so these are the basic integration rules. I put them all on one slide so that way you guys can see them. So you have the constant rule, constant multiple rule, the sum rule, the difference rule, the simple power rule, the general power rule, simple exponential rule, general, and simple log and general log. All of these rules still apply. There are a couple more. You're going to get a couple more before school's out. But all of these rules still apply. In order to get the function that we are going to be evaluating, we need to apply these rules. Instead of having that plus c, we're just going to be plugging numbers in. Okay? So this is the guidelines. Okay, so this is not a procedure for finding the antiderivative. Those are the procedures for finding the antiderivative. Okay, You're evaluating, so your answer is a number. Okay, the constant of integration is dropped because it is neutralized. You have to follow this following notation, which is the integral from a to b of f of x dx is equal to big F of x, which is that antiderivative that you're finding using the rules on the last slide, from b to a, evaluated. And then you plug in b for f of x and plug in a for f of x in order to get your new evaluation. Okay, so this is me showing you that the C can be neutralized. What happens here is you have a distribution. Okay, so you end up getting a negative C, and these will cancel out. Okay, so that's your proof. Okay, so these are some properties of the definite integrals. They mirror the indefinite integral ones. So this is the constant rule. So if I have a constant, I can still pull that constant out. That is exactly the same. Okay, this is the sum and difference rule. It same exactly as the indefinite integral. Okay, now this is an interesting one, and I want you to think about this in terms of a space. So for example, if I had my picture here, so let's make this graph. Okay, so let's say this is my graph, and let me change my pen, going from A to B. Now this is something geometrically that would make sense. So you remember from the last video, I talked about finding areas by splitting things up. So like if we were talking back to 7th grade, if I asked you to find the area of this shape here, you would probably split it up into 5 different pieces and find the area, correct? Now, that really wouldn't work theoretically if you were to have an oblong area, right? Like it's very hard for me to split this up into shapes that would make sense for me to, that one's pretty all right. That would make sense for me to solve for now. But the tool we do have here is mathematically, if I was to split this area into a third space, okay, this area plus this area is still the same area. So this is our method. This is our method here. We have the integral of f of x from a to b is also equal to the integral of a to c of f of x plus c to b of f of x if c is in the middle. Okay, if c is in the middle somewhere. So if you have a c, like so let's say this is 1 and let's say this is 5. This area here is still going, if this was 3, the area of 1 to 3 is plus 3 to 5 is going to be equal to the area of 1 to 5. Okay, but sometimes it's important to be able to split this up, because what if I have an integral that looks like this? Okay, now I'm dealing with a negative area. We're going to tackle that later. But I have a negative area. I said that integrals are only okay if I have a positive area. So this isn't going to work right now. But we're not going to be dealing with those in this. But it will happen. Okay. Now, next one. I have f of a to a of f of x is 0. That makes sense, right? So like, let's say this is my function. Regular. Let's do a straight line, easy. And let's say that this is a here. Okay. If I'm not going anywhere, am I accumulating any area? No, I'm not. Okay, so that makes sense. Okay. Now, here, this is what I was talking about on the last drawing. If I have a negative area, okay, or vice versa, if I have the integral of a to b of f of x is equal to the negative integral of b to a, okay, this is just reversing my order. This is reversing my order of integration, which is thus making a negative area positive in that occurrence. So this is basically saying I can factor out a negative. Okay, that is what this is saying. So for example, let's say that I have a function that looks like this, which should look a little bit like a negative cosine curve here. So if I have, let's say this was A here, and then B was over here. Okay, B was over here. Okay, and what's happening here is I have a negative area from here to here. Okay, I don't want a negative area, but what I can do is I can make this positive by switching the order of integration. Instead of going from A to B, I would go from, or let's call this C. Instead of going from A to C and getting a negative answer, I can go from C to A and get a positive answer and then just multiply it by a negative. Okay. I have to still account for the fact that this is negative, right? If I was to take the total area from A to B, I would have a negative area here, but I would have a positive area here. Okay, and when I add these together, I would still be accounting for the fact that I have a negative area. This is important for when you're like graphing things like loss in a business, right? If we're graphing like total net profit and there's a loss, you're going to have a negative area. Does that still count in your total profit? Yes. Is it going to be more difficult when we're evaluating? Yes, which is why we have this rule here. Okay, so this is a very good rule to be able to use. You are able to factor negatives out if you switch the order of integration. If you switch the order of integration. Okay. So let's do an example really quickly. So this is a more advanced example, and it's not one that is starting from 0. So for example, I have f of x is equal to x squared minus 1, bounded by the lines 1 and 2. Okay, so visually, this is what we're looking at. We have f of x is equal, sorry, I lost my pen. We have f of x is equal to x squared minus 1, and then I have my 2 lines, 1 and 2. So the area here is this area. Okay, so if you're using a visual tool like Desmos, make sure that you're like visualizing what is it that you're looking for, right? So that's what I'm looking for. So the first thing I have to tell myself, I say area, that is a definition of a definite integral. What are the bounds? These are the bounds, right? So this is the lower limit, and then this is the upper, right? So naturally, the upper is going to be the rightmost bound. So the rightmost bound in this case is 2. And then the leftmost bound is going to be the lower limit, which is 1. Okay, so I find the antiderivative. I use my simple integration rule, to find this first antiderivative. So I have 1/3 x cubed. I check that. If I take this, do I get x squared? Yes. Okay. Minus x. What's the derivative of x? 1. I have a minus. Minus. It works. Okay. Now what I'm doing is I'm applying the fundamental theorem of calculus. I'm saying that 1/3 x cubed minus x evaluated from 2 to 1, right? Where f of 2, this is the upper, goes first. Okay. And then the lower goes second. Okay. And then I evaluate. Okay, I plug in 2 for all areas. So I have 2 cubed is 8, 8/3 minus 2 minus f of 1. 1 cubed is 1, 1/3 minus 1. And then I just evaluate. My answer is 4/3. But because I'm talking about area, it's 4/3 square units. Okay, so you have to make sure that you're taking into account that you're having the squared unit because you're talking about an area. Okay, so now evaluating a definite integral without a picture, algebraically. Okay, so you're evaluating the definite integral from 0 to 1 of f of t plus 1 squared. Whew, That means that I'm going to have to use a couple of rules here. Okay. Here I have a composition of functions. That means I have a function being plugged into another function. This is a x squared body, right? So you see like x squared, that's a body of an x squared. So that means I have a u and a du. This is a u substitution problem. This means that there's a chain rule here. Okay. If there's a square here, that means that there's a chain rule happening. So I identify u and I identify du. So u is 4t plus 1, and then du is going to be 4t dt. So that means I have a 4, or I need a 4, and I have 1. So remember, there's a 1 here always. So that means I need to insert a 1/4 and a 4. Okay, so it's the same way that I did it when I had an indefinite integral. I inserted a 1/4 and I inserted a 4 here. Okay, so now I can see a little better that I have my du. Okay, and then I also have my u present. Okay, so when I do my u substitution, I'm going to integrate and I'm going to substitute in. Okay, I'm going to pull the 1/4 out, which is why the 1/4 is here. I have a u squared du, okay, is equal to the 1/4 carries over. I'm going to highlight that in yellow. Okay, this 1/4 just gets carried over here, and then we integrate. So I have 1/3 u cubed, which is my simple power rule, and then that's going to be equal to 1/4 times a third, 4t plus 1 cubed, from 1 to 2. Okay, so now what I'm going to be doing is, this is a number. Okay, this is a number. Okay, so just be aware of that. So what I'm doing is I'm applying this fundamental theorem of calculus to this. I'm plugging in 1, and then I'm plugging in 0, and then I'm subtracting those two evaluations. So I have 125 over 12. I have 1 times 4 is 4. 4 plus 1 is 5. 5 cubed is 125. 125 over 12 minus, okay, so that's 1. That's the evaluation of 1. Minus 112, because I plug in 0. 4 times 0 is 0. 0 plus 1 is 1. 1 cubed is 3, or 1 cubed is 1. 1 over 1 times 1/12 is 112. 125 over 12 minus 112 is 124 over 12. Whew, is equal to 31 over 3. Now remember, 31 over 3 is an area. Now that we know that, and we're evaluating, we have to make sure we have a square units under there. Okay. Now, if we're talking about a real world application, those squared units would look like rates, right? So they would be like, for example, if we were doing like population over time. Okay. Let's say that this is an exponential. Okay, and we're finding this area. So we find this area, let's say it would be, let's say it's 15 mil. Okay, so it would have to give context. So if this was a 5-year time period, you would say it's 15 million people over 5 years. Okay, so I think that this tool really starts to open up a lot of possibilities for data science here, because what it does is it allows us to take abnormal functions and find out accumulations over time, and give context to those very odd problems. Okay, but that's it. Look out for your assignment. Please come to my calculus chat tomorrow. I'm looking forward to talking to all of you. Please feel free to contact me with any questions. Ah.